Now we're moving on to the lateral area and surface areas of right cones. So how are we going to do that? Well, clearly there's a circle on the bottom. We know how to get the area of that piece. But what about the lateral surface going around the cone? Not the circle, but the rest of it. What shape is that? On a previous video, I showed you that the lateral part of a cylinder, that paper towel I had, is really just a rectangle if you unfold it. What shape is this thing if we unfold it? Guesses I usually get when we're in school, the first guess I get is a triangle, but if you cut out a triangle and try to fold it without any overlapping parts, it doesn't create a cone. And then people usually guess trapezoids, and that doesn't work either. Here's the answer. It's actually a sector of a circle. So I'm going to show you how if you take a circle and cut out two radii, whether it's a small piece or two collinear radii, a semicircle, or you cut out a big piece, these are all sectors of circles. And watch what happens when you push the two radii together. You get a nice cone, also a nice little hat. So this radius of that circle is now the slant height of the cone. Here's another one. If I take a sector of a circle and I push the two radii together, creates a perfect cone. And even a semicircle. If we push the two radii together, we in fact get a cone. So that's what the shape is. So we have to figure out how to get the area of that. And again, the hard part is the lateral area. The surface area, once we know the lateral area, surface area just means add the circle on the bottom. So let's figure out how to get the area of that lateral surface, that sector of the circle. So to be clear, I'm going to say that this point is A, the top of the cone is A, and this is B. So there are two different circles involved here. There's the circle that makes, there's this circle, the lateral surface that makes the lateral part of the cone. So there's this circle, it's really a sector of a circle. But then there's a different circle on the bottom of the cone, right? So I'm going to call the lateral surface of the cone sector A. So this shaded piece represents something like this. And that point A does become the vertex of the cone when we make the cone, right? So this is point A, the vertex of the cone. It's the center of that circle. And point B is the center of the base. So how do we get the area of this shaded sector? As long as you understand this top equation, the rest is just some algebra, and it works out quite nicely. It takes a little bit of thinking to understand this first line here. But what this line is saying is this: whatever fraction of the circle's circumference I have here is equal to the fraction of the area that I have. In other words, if this is a 90-degree angle, that means this is 3/4 of the circle's circumference, but this is also 3/4 of the circle's area. Same thing here. The length around this sector is half of the circle's circumference, and the area of this sector is also half of the area. If this is 2/3 of a circle's circumference, then this is 2/3 of the circle's area. So I don't know if that's back in frame or not. That's what this top equation is saying. The area of this sector compared to the area of the whole thing is the same as the length around the sector over the length around the whole thing. So maybe they're both 3/4, maybe they're both 1/3, maybe they're both 1/2, but whatever this fraction is, area of sector to area of hole, it's going to equal the length around the sector to the length around the hole. That's that equation. And our goal is to figure out the area of sector A. Well, the area of sector A, as we said, is the lateral area when you twist it into a cone. So I replaced this with lateral area cone. The area of circle A, the area of this circle is, let's see, well, the area of any circle is pi r squared, but in this case, remember, that radius is really the slant height of the cone. So I'm going to call it L for slant height of the cone because that's what it's called up here. So the area of the circle is pi times its radius squared, and its radius is the slant height, so pi L squared. The length around sector A, so this also is a little interesting. So how long is this? What happens on this paper when I make the cone? What does this arc length become? Let me hold it like this, So what does this length become when I make the cone? It becomes this. That's the circumference of the base. So the length around sector A is the circumference of the base, the circumference of circle B. And finally, what's the circumference of circle A? The circumference of this circle? Well, the circumference of any circle is 2 pi r, except remember, this radius is really an L. So you'll see down here, I'm calling it 2 pi L. All right, so this is all just some substitution. You can go back and watch that again. I did replace circumference of circle B with 2 pi r. And circumference of circle A with 2 pi L. And then I cross-multiplied, I didn't cross-multiply, but I multiplied both sides times pi L squared because I want to solve for lateral area of a cone. So to get rid of that denominator, I multiply both sides by pi L squared so that it cancels on this side and it pops up on this side. You'll also see that the 2's cancel and the pi's cancel. So here's the pi L squared that was in the denominator here. When I multiply both sides by pi L squared, it pops up in the numerator over here. So pi L squared times that radius, and there's an L in the denominator. L squared, of course, is L times L. I just wrote it out to show you that that L and that L would cancel. So the final formula is pi r L. The lateral area of a cone is pi times the radius of the base times the slant height. That is the hardest one to derive in the whole chapter, but there it is. And of course, if we want the surface area, we would just add pi r squared. We would add the area of that. I actually wrote it down here. So there are the two formulas we just came up with, and now we're going to try using them in a few examples. Example number 1. Find the lateral area and surface area of each right cone to the nearest tenth. So we're going to round off to the nearest tenth. So you've got your formulas. Lateral area is pi RL, surface area is pi RL plus pi r squared. You can hit pause. All right, so we need the radius, which of course is 3 if the diameter is 6. And if the height is 5, then the Pythagorean theorem can be used to get the slant height. 5 squared plus 3 squared equals L squared, and it comes out to be root 34. And now I've got all the numbers I need. Pi RL, so pi r L is root 34. 55.0 to the nearest tenth, yards squared. And for the surface area, it's pi RL, there's the R and the L, plus pi times that radius squared. 83.2 yards squared. So that was a pretty straightforward one. Here's number 2. So if you know the circumference of the base and the slant height, what's the lateral area and surface area to the nearest tenths? All right. So again, we need to figure out the radius. And if the circumference is given, and we know the circumference formula is 2 pi r, then I can replace the circumference with the given circumference that was 3 pi. So I want to solve for radius. Divide both sides by 2 pi. Radius is 1.5. And now we're home free. We got the radius. The slant height was given to be 5. So pi RL for the lateral area, 23.6 feet squared. And pi RL plus pi r squared. So again, just substituting 1.5 for the radii and 5 for the slant height, and you should get 30.6 feet squared. All right, 2 down, 2 to go. How about if you know the height and the area of the base? Height is 3, area of the base is 10 yards squared. So you can hit pause and try that one. Now here, there may be some calculator issues. I'm going to try to show you on my calculator how tricky these can be to enter into your calculator. So for starters, I drew what was given, the height of 3, and I wrote out my area formula, pi r squared, because I was given the area to be 10. So I can substitute 10 for my area, and I can solve for radius. First, I divide both sides by pi. So the radius squared is 10 over pi. And then to get the radius, I have to square root both sides. So the radius we're going to be working with is the square root of 10 over pi. Not a very friendly number, but that's what it is. So now I knew my radius, but I still didn't know the slant height. We need the slant height for our formula. So that's where we use the Pythagorean theorem again. Leg squared plus leg squared equals hypotenuse squared. So 3 squared, 9. Root 10 over pi squared, remembering square roots and squares are inverse operators, is 10 over pi equals L squared. So if this is L squared, then L is just the square root of this. So we have an ugly slant height and we have an ugly radius. But we don't want to round them off because our answer will come out further off than it should be if we do that. So now it's just a matter of substituting into the formula and being careful with the calculator. So you can get a shot of that, and I'm going to show you what this looks like on the calculator. Let's see, pi, here we go. And it really is worth, as I'm doing this, making sure that you can type this into your calculator correctly, because a lot of students struggle with this. They think they can do it, and then they go to do it, and they're getting wrong answers, and the hands go up in the classroom. 10 over pi. All right, so here it is in the calculator. What I really want you to notice is for every open parenthesis, there needs to be a closing parenthesis. So when I hit my square root button, and I have that open parenthesis for my my radius of root 10 over pi. When I finish typing in 10 over pi, I have to close that parenthesis. So the same thing when I put in my slant height of root 9 plus, what was it, 10 over pi. Notice I have a closing parenthesis there. Now, trickier than this is going to be, now I'm going to do the surface area. I'm going to add, and I'll have to take the calculator out of frame for a second. Oh, I take it back. I don't have to do anything tricky. Because if you're, I mean, you could try typing this all in the calculator, but there's no need to fill in that radius of root 10 over pi and get the pi r squared portion of our surface area formula, because pi r squared, think about what that represents. That represents the area of the base. We were given the area of the base. It's 10. So sure, if you substitute the radius that we got of square root of 10 over pi in here, all of this will come out to be exactly 10, but why bother? If you're really paying attention, you'll recognize, oh, we know this number is 10. So if we just add 10 to our lateral area, we will get our surface area. Okay, I have one more. Maybe two. I might have lied. All right, I've got two more for you. How about this? Find the surface area of this solid, a cone sitting on top of a cylinder. Notice it doesn't say to round. So when I do this one in the classroom, a lot of times students will suggest, well, since we want the surface area, just get the surface area of the cone plus the surface area of the cylinder and add them together. That doesn't work, because if we were to drop this object into a bucket of paint, whatever gets paint on it is what's considered on the surface. This circle is not on the surface of that solid. And if we just do surface area of cone, we'd be including that circle. And if we do surface area of cylinder, we're including that circle. But that circle should not be included. So instead, we want the lateral part of the cone, the lateral part of the cylinder, and that one base down at the bottom. So here it is. Lateral area of cone plus lateral area of cylinder plus the one base at the bottom. Now, we were given the radius to be 3. Where did I get the slant height of 5? Well, if we look back at the picture, I see the height of the cylinder is 2. I see the height of the whole object is 6. So that means that the height of the cone must be 4. Right? 4 plus 2, the whole height is 6. So let's draw that height in a convenient place. 4. Remember, this radius is 3. So Pythagoras would tell us that slant height is 5. Pythagorean theorem. So that's where the 5 came from. And again, the radius is 3, the height of the cylinder is 2, and pi r squared for the base. So it's lateral for the cone 15 pi, lateral for the cylinder 12 pi, the base is 9 pi. They're all like terms. They add up to be exactly 36 pi feet squared. Okay, last one. What's the diameter of a right circular cone if you know the surface area to be 65 pi and a slant height to be 8 centimeters? This should say centimeters squared. Surface area of 65 pi centimeters squared and a slant height of 8 centimeters. What's the diameter? So this is similar to a problem I did in the cylinder video. If we know the surface area, let's start with the surface area formula for a cone. Pi RL plus pi r squared. And I'm going to substitute all the values I know. I know the surface area is 65 pi. I know the slant height is 8. And this equation now only has one unknown value in it, the radius, because again, like before, remember pi is not a variable, pi is a number. So this is just an equation to solve for r. All these terms have a pi factor, so we could divide each term by pi to get a simpler equation. It's quadratic. Subtract 65 from both sides to create the 0 that we need. You can try to factor it. It is factorable, but if you don't know how to factor, you'll be doing tons of it in Algebra 2. Quadratic formula. A is 1, B is 8, C is negative 65. And you can pause the video if you need to check out my work. You do wind up with 2 solutions, but the radius can't be negative. So if the radius is 5, the answer to the question is the diameter is 10 centimeters. All right, good luck with your problems.